Somewhere behind the sun, a rock is being slowly baked to pieces. We have never seen it. We have never photographed it. We don't know its exact size, its exact shape, or its exact orbit. But we now know, thanks to a peer-reviewed paper that dropped 5 days ago, that it is real. It is shedding pieces of itself into Earth's path, and we have been flying through its crumbs for the last 3 weeks. And that fireball swarm this channel has been documenting since March, the one the American Meteor Society just confirmed as a 4.5 Sigma anomaly, may have finally, for the very first time, been handed a peer-reviewed partial explanation. In the next 24 hours, 2 visible asteroids will skim past us closer than the Moon. They are the distraction. The invisible one is the story. Stay until the end, because what this discovery says about everything else hiding out there is the part nobody's talking about yet. If this has you hooked, hit like and subscribe to the Skylab, because you're going to want to be here when the next batch of data comes in. Drop a comment below. I genuinely want to know where in the world you're watching this from, what time it is there, and your honest answer to this. If one invisible asteroid hidden behind the sun has been quietly feeding debris into Earth's path for weeks without a single telescope on this planet ever catching it in the act, how many more do you think are out there right now, doing the exact same thing in the exact same blind spot that we have not noticed yet? Let me know what you think. Now, let's get into it. Part 1. The convergence nobody was supposed to notice. 2 asteroids will skim past Earth inside the next 24 hours, and neither one of them is the story. Let that sink in for a moment, because it goes against every instinct you have about how space news is supposed to work. Normally, when a rock the size of a building comes closer to us than the Moon, that's the headline. That's the thing we're supposed to be watching. That's the thing that makes your phone buzz at 2 in the morning with a push notification dressed up in red text and exclamation points. But tonight, as I'm recording this, 2 of them are about to do exactly that back to back within a single rotation of our planet, and I'm telling you right now that they are not what we need to be talking about. They're the distraction. They're the thing your eyes are drawn to while something far stranger, far quieter, and far more consequential is unfolding just out of frame. Between 8 in the morning Saturday and 3 in the afternoon Sunday, 2 separate asteroids are going to slip past Earth closer than the Moon. The first one is called 2026 HQ. It's going to cross our path at a distance of 0.43 lunar distances. The second one is called 2026 HJ, and it's coming in even closer at 0.30 lunar distances. For those of you who prefer your numbers in miles, that's about 160,000 miles for the first one and roughly 115,000 miles for the second. In cosmic terms, that's the equivalent of 2 strangers brushing shoulders in a hallway. In human terms, it's still a very long way away. You are not in danger. Your dog is not in danger. Your plants will be fine. But here's the part that starts to itch. Both of these asteroids were discovered only weeks ago. Not years, not decades, weeks. They were nowhere in our catalogues at the start of the year. They weren't on anyone's radar. They weren't being tracked, monitored, modelled, or predicted. And then, within a narrow window of observation, they both appeared. They were both flagged as close approaches, and they're both now sliding past us like they had always been on the schedule. Because to the universe, they always were. We just didn't know about them yet. Now, before your pulse climbs too high, let me ground you in something important. Sublunar flybys, meaning asteroid passes that happen closer to Earth than our own Moon, actually happen multiple times per month. They are, statistically speaking, routine. They are cosmic background noise. The universe is messy. Our orbital neighbourhood is full of small bodies tumbling along their own paths, and every few weeks one of them wanders into our address. Most of the time, nobody notices. Most of the time, only astronomers and tracking systems take any interest at all. The public rarely hears about them because the math says they're fine, and the math is almost always right. So 2 asteroids passing us in 24 hours isn't, on its own, a crisis. It isn't even, on its own, particularly unusual. What makes this unusual is the timing, because 5 days ago, buried in a peer-reviewed paper in the Astrophysical Journal, a NASA scientist quietly announced something that most of the news cycle hasn't caught up with yet. Earth, it turns out, has spent the last 3 weeks moving through the debris trail of another asteroid. Not one of the 2 we can see, a third one, a hidden one. An object that has never been directly observed, that is not in any catalogue, that has no image, no confirmed orbit, no identification number, and no way to be tracked from the ground, because this object, whatever it is, lives in a place we cannot look. It lives inside the glare of the sun. Think about that for a moment. While we've been watching the two asteroids we can see march closer to us, a third object, which we cannot see at all, has been shedding material into our path for weeks, and we only found out about it because that material has been burning up in our sky. That's what today is really about. It's not about the two rocks that are going to sail past us. It's about the one we missed. It's about the one that never showed up on any telescope because it's been hiding in a blind spot we have never been able to penetrate. And it's about the fact that we are only now, just in the last few days, starting to piece together evidence that it exists at all. I want to introduce you to another thread that's going to run through this entire story, and that's the fireball anomaly. Since March, the American Meteor Society has been logging an unusual increase in bright meteors, long-duration fireballs, and even physical meteorite recoveries. By the time Q1 of 2026 was done, they had classified the anomaly at 4.5 sigma. In statistics, 4.5 sigma means there's roughly a 1 in 200,000 chance this happened randomly. That's not a fluke. That's a signal. And that signal has been building for weeks with no confirmed cause. Until now. Until this paper. Until this hidden object. And running underneath all of this, racing ahead of the peer-reviewed science, is a viral narrative. You've probably seen it. Posts claiming Earth is flying through a cloud of debris. Videos warning of incoming disaster. Comment sections full of apocalyptic predictions. The truth is more interesting than the panic, but the panic is moving faster because the truth requires sitting with uncertainty and the panic doesn't. So here's the tension I want you to hold in your head for the next 2 hours. Are these separate events stacked on top of each other by coincidence? Two flybys happen, a paper drops, a fireball surge happens to be underway, and we're all just pattern matching the way humans always do? Or is this one system, slowly becoming visible through its effects, finally letting us see a population of objects we have been missing this entire time? Because the central question isn't whether any of this is going to hurt you tomorrow. It won't. The central question is about detection. How much of what shapes Earth's local environment are we actually seeing? And how much is moving through our space, past our planet, and into our upper atmosphere without ever being catalogued, photographed, or named? The object we can't see is the only one that's actually doing anything to Earth right now. The two we can see will pass us and leave. The one we can't see has been feeding our sky for 3 straight weeks. Over the next 12 parts, we're going to follow the trail backward. From the flash in the sky, to the debris stream, to the invisible parent, to the blind spot it lives in, to the implications of what that blind spot contains. We're going to talk about rock comets and sunward telescopes. We're going to talk about a NASA scientist and a dataset spanning 4 continents. We're going to talk about what this means for planetary defense and what it means for what we've already been moving through without ever seeing. Because here's the uncomfortable truth at the center of all this. We are not reacting to what's coming toward Earth. We are reacting to what Earth has already been moving through without ever seeing it. And that changes the shape of the entire conversation. Stay with me, this gets stranger. Part 2. The flybys are routine. The timeline isn't. Let me walk you through the 2 visible actors in this story first, because before we chase the ghost, we have to understand why the 2 rocks we can see are actually the least interesting part of the weekend. They are, in a very real sense, stage lights. They illuminate the scene, they draw the eye, they make you pay attention to the sky. But they are not the performers. They are not even part of the same show. 2026 HQ is the first to arrive. It comes in at 0.43 lunar distances, which works out to roughly 160,000 miles from Earth's surface. That's comfortably farther than the Moon, but well inside the threshold astronomers use to flag something as a close approach. HQ is estimated to be somewhere in the range of a small to mid-sized asteroid, big enough to cause serious local damage if it hit, but small enough that its trajectory never actually intersects us. Its path is clean, its geometry is well understood, at least well enough for us to know it's not going to hit anything. It will come, it will go, and within a week, it will be gone from most news cycles entirely. 2026 HJ is the second act. It's coming in tighter, at 0.30 lunar distances, roughly 115,000 miles out. It's travelling at a velocity of about 6.48 kilometers per second relative to Earth, which is typical for objects in this class. For context, that's about 14,500 miles per hour. HJ is in the size range where comparisons to the Chelyabinsk meteor start to make sense. Chelyabinsk, if you remember, was the object that exploded over Russia in 2013, the one that shattered windows across an entire city and left people with glass cuts they didn't expect to get on a Tuesday morning. That object was about 20 meters across. HJ is in a similar size category. If HJ were actually on a collision course, we would be talking about an airburst event, not a global catastrophe, but a serious regional one. But HJ is not on a collision course. Its trajectory is safe. The math is clean. The sky above you tomorrow will not change because of it. Here's what should bother you though. Neither HQ nor HJ has received detailed radar imaging. We don't have high-resolution shape models for either of them. We don't know their rotation rates in any detail. We don't know their surface compositions. We know they exist. We know approximately how big they are, and we know where they're going. That's it. That's the entire file. And that file was only opened a few weeks ago because that's when we first saw them. This is the detection lag, the gap between when an object actually enters our observational range and when we actually register that it's there. And for these two, that gap closed just in time. We saw them, we tracked them, we confirmed they were safe. The system worked in the minimal sense that it could work. But here's where the numbers should start to make you feel a little smaller. NASA estimates that there are roughly 15,000 undiscovered asteroids out there that are 140 meters or larger. Let me say that again so it lands properly. 15,000 objects big enough to wipe a city off the map. Objects that, if they hit water, would generate tsunamis that would reshape coastlines. Objects that we have right now no idea exist. And that's just the big ones. If you scale down to the Chelyabinsk class, objects in the 20-meter range, the estimated undiscovered population is in the hundreds of thousands, possibly more. These objects are small, they're dark, they're fast-moving, and they reflect very little sunlight, which makes them extraordinarily difficult to pick up on our telescopes. You basically have to get lucky. You have to catch them in a specific orbital configuration, where they're far enough away to be tracked, but close enough to be visible against the background of space. I want to introduce you to a concept that I think is going to help you make sense of this entire story. I'm going to call it routine invisibility. The idea is simple. For the vast majority of the time, for the vast majority of these objects, we cannot see them. They are in parts of the sky where our instruments can't reach. They are at sizes where our sensitivity falls off. They are moving in directions that hide them from our cameras. They exist. They are doing things. They are influencing our orbital environment. But they are, for all observational purposes, invisible. And this creates a psychological mismatch that I think explains a lot of why moments like this one feel so jarring. To a scientist, HQ and HJ passing us this weekend is completely routine. This kind of thing happens often enough that it barely registers inside the planetary defense community. It's a Tuesday. But to the public, finding out that two asteroids you'd never heard of before are going to skim past Earth inside 24 hours sounds like something out of a movie. The event is simultaneously ordinary and shocking, and both interpretations are correct depending on where you're standing. Now, I want to be very clear about something, because I don't want you to lose the thread. HQ and HJ have nothing to do with the hidden asteroid we're going to spend most of this video discussing. They are not part of the M2026A one debris stream. They are not connected to the fireball anomaly. They are not fragments of the rock comet we're about to meet. They are simply unrelated objects that happen to be passing us at the same time the real story is unfolding. But their value to this story isn't in what they are, it's in what they represent. Because if two objects we didn't know existed a month ago can approach Earth this closely, and we only spot them in time to confirm their safety rather than track them over a full orbital period, what does that tell you about our observational completeness? It tells you our catalogue has holes. It tells you objects can and do arrive from observational blind zones without warning. It tells you that, for objects in this size class and smaller, discovery often happens right at the edge of what's possible, sometimes within days of closest approach. And that is exactly how the hidden asteroid we're going to talk about has been avoiding detection this entire time. It lives in one of those blind zones. Not the same kind that HQ and HJ used to sneak up on us, but a much more specific, much more permanent, much more systematic one. It lives somewhere we have not been able to look. It lives inside the sun's glare, and while we've been busy watching the two we can see, it's been doing something the other two haven't been doing at all. It's been shedding pieces of itself into our path. Part 3. The story behind the story. The paper dropped 5 days ago, and if you don't follow planetary science press releases, you probably missed it. Most people did. It didn't trend on any of the big platforms. It didn't crack the mainstream news cycle. It was published in the Astrophysical Journal, which is one of the most respected peer-reviewed journals in astronomy, and then it just sat there, waiting for someone to notice what it actually said. The author is Dr. Patrick Schober, a researcher at NASA's Johnson Space Center. Schober's specialty is meteor orbits, and the connections between meteor streams and their parent bodies. If you've never thought about that as a field of study, you're not alone, but it's a genuinely fascinating niche. Every meteor that burns up in our atmosphere came from somewhere. It was once attached to a larger object, and that larger object had its own orbit around the Sun. And if you can work backward from the meteor's path to the parent's orbit, you can start to build a map of where all this stuff is coming from. What Schober did in this paper was take a massive data set, pulled from global meteor monitoring networks across Canada, Japan, Europe and California, and comb through it looking for statistical clusters. A meteor shower at the most basic level is just a cluster. It's a group of meteors that all share similar orbital parameters, meaning they all came from the same source. The Perseids, which you've probably heard of, are a cluster tied to Comet Swift-Tuttle. The Leonids are tied to Comet Tempel-Tuttle. Every major meteor shower has a parent. When Schober ran his analysis, he found something new. 282 meteors, spread across multiple networks, sharing orbital parameters so similar that the probability of the clustering being random was statistically negligible. These weren't random background meteors. These weren't leftovers from known showers. These were something else. Something that hadn't been identified before. And because it hadn't been identified before, it needed a name. The stream was designated M2026A1. The M stands for meteor stream. The 2026 is the year. The A1 is the sequence designator, meaning it's the first new stream confirmed this year. It's a clinical name for a very strange object, because what Schober found wasn't just a new shower. It was a shower with properties that pointed back to a parent body that had never been observed. The orbital parameters the meteors shared told an unusual story. The perihelion of the stream, which is the point where the orbit comes closest to the Sun, was calculated at approximately 0.22 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, so 0.22 astronomical units means about 22% of the Earth-Sun distance. That's extraordinarily close. That's closer to the Sun than Mercury ever gets. At that distance, solar heating is brutal. Surface temperatures on anything that orbits that close would climb into the hundreds of degrees Celsius. Rock becomes stressed. Volatiles get cooked off. Any object that loops in that close repeatedly is going to experience serious thermal abuse. This is important because most asteroid-derived meteor streams don't have perihelion values this extreme. When you find a stream with a perihelion this close to the Sun, you're looking at something special. You're looking at an object that spends part of its orbit in a zone where the physics gets strange. The radiant of the stream, meaning the direction in the sky the meteors appear to come from when you project their paths back, fell near the boundary region of the constellations Virgo, Corvus, Libra, Centaurus, and Lupus. That part of the sky, at the times these meteors were observed, corresponds to a specific geometric relationship with Earth's orbital motion. Radiant information matters because it constrains the source. You can't have an arbitrary parent body producing these meteors. The parent's orbit has to intersect Earth's orbit in a specific way, at a specific geometry, to produce meteors that appear to come from that direction. And when Schober worked the math backward, he found that the parent body this stream had to come from was an object on an orbit that passed close to the Sun, on a track that crossed Earth's path in a very particular way. That orbit was calculable. The object's rough properties could be inferred, but the object itself had never been seen by any telescope. Ever. Let that settle for a moment. We have confirmed the existence of an asteroid through the debris it's leaving behind without ever having directly observed the asteroid itself. This is what I'm going to call reverse detection. It's the inverse of how we normally find things in space. Normally, you see an object, you calculate its orbit, you predict its effects, and then you watch to see if your predictions hold up. Observation first, inference second. Reverse detection flips that. You observe an effect, you work backward to the cause, and you infer the existence of something you've never seen. The philosophical weight here is heavier than it might sound at first. We are declaring the existence of a physical object based entirely on the pattern of its consequences. There's no image, there's no radar return, there's no spectroscopic signature of the body itself. There is only the river of dust and rock it's leaving in its wake, which happens to be flowing through our corner of space. This isn't unprecedented in science. We've inferred the existence of exoplanets from the wobble of their parent stars. We've inferred the existence of dark matter from the rotation curves of galaxies. We've inferred the existence of subatomic particles from the tracks they leave in detectors. Inference is a perfectly valid method of detection when the evidence is strong enough, and in this case, the evidence is strong enough. 282 meteors, all pointing back to the same source, on orbits that cannot be explained by any known object, is a signal, not a noise. But inference can only tell you so much. It can tell you something is there. It can't tell you what colour it is, how fast it's spinning, what its surface looks like, or how stable it is. All of those questions require direct observation, and direct observation for this particular object is currently impossible because of where it lives. Which brings us to the mechanism. How does an asteroid, which is just a big dry rock, produce a meteor stream in the first place? Comets do this all the time. That's how most meteor showers form. A comet swings through the inner solar system, the sun heats it up, its ice sublimates, it vents gas and dust, and over time it leaves a debris trail behind. When Earth's orbit crosses that trail, we get a shower. But asteroids aren't supposed to do this. Asteroids don't have ice, they don't vent, they don't have the volatile chemistry that lets comets throw material off their surfaces in the amounts needed to form visible streams. Or do they? Part 4. A new class of object. The textbook definition of a comet involves ice, frozen water, frozen carbon dioxide, frozen methane, frozen ammonia, the full menu of volatile compounds that exist in the outer solar system, where it's cold enough for them to stay solid. When a comet swings inward toward the sun, those ices start to sublimate, meaning they transition directly from solid to gas without going through a liquid phase. The escaping gas drags dust with it, and that combination, gas plus dust, is what creates the glowing coma and the long tail that make comets look the way they look. Asteroids, in the textbook definition, are not supposed to do this. Asteroids are rocky bodies, they're dry. They're leftover debris from the inner solar system where temperatures were too high for ices to form in the first place. An asteroid, in principle, should just sit there being a rock. It shouldn't throw material off its surface. It shouldn't have a tail. It shouldn't produce a meteor stream. And yet, over the last few decades, astronomers have been quietly documenting a class of objects that breaks this rule. Objects that are classified as asteroids, in the sense that they're rocky and they lack obvious ice, but that nevertheless behave like comets. They produce dust, they show activity, they leave trails, they feed meteor streams, and the question of why has been one of the more interesting puzzles in small-body astronomy. The answer, it turns out, is thermomechanical stress. It's a mouthful, but the concept is intuitive if you've ever dropped a cold glass into hot water or watched a ceramic plate crack under a temperature change. Rock, when it gets heated, expands. When it cools, it contracts. When it does this over and over and over again, especially in the presence of gradients, meaning one side hot and the other side cold, the internal stresses build up and the rock cracks. Fractures form, material flakes off, pieces break loose. Now apply that process to an asteroid that orbits the Sun at a perihelion distance of 0.22 astronomical units. Every time that asteroid swings in close, its sunward face gets baked to temperatures that can exceed 700 degrees Celsius. Its anti-sunward face, the one facing away, stays much cooler. The gradient across the object is enormous. The thermal stress is extreme, and this happens on every orbit over and over for hundreds, thousands, tens of thousands of years. Under those conditions, rocks don't just sit there and take it. They crack, they spall, they shed layers. Small particles work loose from the surface and get nudged outward by radiation pressure. Larger chunks can break free under the stress of thermal cycling. The object slowly is being disassembled by the Sun itself. There's a second mechanism on top of this, and it involves sodium. Sodium is a metal that, under extreme temperatures, can vaporize directly from the surface of the rock. When you heat the sunward face of one of these objects hot enough, sodium atoms start to boil off. That sodium vapor creates its own kind of gas pressure, and that gas pressure can help lift small particles of dust and rock away from the surface. It's not the same mechanism that drives cometary activity, which involves water ice, but the outcome is similar. You get material ejected from the surface, you get a dust trail, you get, eventually, a meteor stream. The canonical example of this kind of object is 3200 Phaethon. Phaethon is one of the strangest bodies in the solar system. It was classified as an asteroid when it was discovered, based on its rocky spectrum and its lack of obvious ice. But it has a perihelion distance of 0.14 astronomical units, which is even closer to the Sun than our hypothetical M2026A1 parent. And Phaethon, despite being an asteroid, is the confirmed parent of the Geminid meteor shower, which is one of the most reliable and spectacular showers of the year. The Geminids were a mystery for decades. Every other major meteor shower had a comet parent. The Geminids didn't. And then astronomers identified Phaethon, worked out its orbit, and realized that the shower and the asteroid shared the same orbital path. Phaethon was the source. An asteroid was feeding one of the best meteor showers on the calendar. The question became, how? The answer, over years of follow-up observations, turned out to be that Phaethon is a rock comet. It's an object that behaves like a comet, in the sense that it produces a debris stream, but the mechanism is thermal stress and sodium vaporization, rather than ice sublimation. Phaethon showed faint activity when it was observed near perihelion. Its emissions turned out to be sodium-dominated rather than water-dominated. And crucially, the amount of dust Phaethon produces in any single orbit is small, much smaller than what a comet would produce. Too small, in fact, to account for the full Geminid stream in any reasonable time frame. What that means is that Phaethon isn't dumping material all at once. It's leaking. It's losing tiny amounts of mass on every perihelion passage, and those losses accumulate over thousands of years. The Geminid stream isn't the product of a catastrophic event. It's the product of slow, steady disintegration over geological timescales. This is the template for understanding what's happening with the hidden parent of M2026A1. The parent object is almost certainly a rock comet, similar in class to Phaethon, possibly smaller, possibly younger, possibly on an orbit that's evolved differently, but operating on the same principles. It swings in close to the Sun, it experiences brutal thermal stress, sodium vaporizes off its surface, small particles get lofted free, larger chunks occasionally break loose under the pressure of thermal cycling, and over time a debris trail forms along its orbit, and that trail eventually intersects ours. The implication for detection is profound, and this is where we start to circle back to why we can't see this object directly. Rock comets produce very little dust compared to their icy counterparts. Their activity is subtle. Their brightness enhancement near perihelion is small. If you point a telescope at Phaethon when it's far from the Sun, it just looks like any other dark asteroid. You'd never guess, from its appearance alone, that it was shedding material into a meteor stream that produces hundreds of visible fireballs every December. What this means practically is that the standard detection strategies, the ones optimized for finding comets with bright comas and long tails, don't work well for rock comets. These objects are dim, they're rocky, they reflect little light. And the part of their activity that would give them away, the subtle vaporization near perihelion, happens in a part of the sky we physically cannot observe from the ground. There's also a secondary process that can accelerate disintegration. It's called rotational spin-up. As small particles fly off an asteroid asymmetrically, they can impart torque to the parent body. Over time, that torque can cause the object to spin faster and faster. Eventually, if it spins fast enough, centrifugal force exceeds the object's self-gravity, and it starts to tear itself apart. This is actually the leading theory for why some rock comets eventually fragment, and it's one of the mechanisms that produces the smaller meteoroids that end up in streams. So when Earth passes through the M2026A1 stream, what we're actually intercepting is the cumulative output of this slow, multi-mechanism disintegration process. We're not catching a single dramatic event. We're catching material that's been shed over centuries, possibly millennia, from an object that has been quietly cooking itself to pieces in the sun's glare for longer than human civilization has existed. The rock-comet process is ongoing, it's slow, it's steady. And critically, for us, it happens in a place we cannot look, which raises a question that, by now, should be starting to feel heavy. If this object is actively producing debris, if it's been producing debris for a very long time, if its parent orbit and its radiant and its perihelion are all calculable, why has no telescope ever seen it? The answer has to do with geometry and with a kind of blindness that is built into the way we look at the sky. We are not missing this object because we aren't trying. We are missing it because by the very design of our instruments and the very position of our planet, we literally cannot look where it lives. Part 5. The Sunward Blind Spot. To understand why we can't see the hidden parent of M2026A1, you have to understand the geometry of observation, and the geometry of observation from the ground is surprisingly restrictive once you actually start thinking about it. When you're a ground-based telescope on Earth, your view of the sky is constrained by a simple fact. The sun is incredibly bright. Objects near the sun from our line of sight get washed out by that brightness. The sun isn't just a light source, it's an overwhelming light source. It's so bright that even a few degrees away from it, the sky glows with scattered light that drowns out almost everything else. This is why you can't see stars during the day. It's not that the stars aren't there, it's that the sun's light, scattered through Earth's atmosphere, creates a wall of brightness that no star can punch through. Astronomers measure a concept called solar elongation, which is just the angle between the sun and whatever object you're trying to observe, as seen from Earth. If an object has a solar elongation of 180 degrees, it's directly opposite the sun in our sky, meaning it's only visible at night, and it's in the darkest, cleanest part of the sky. Easy to observe. If an object has a solar elongation of 90 degrees, it's at a right angle to the sun, which means it's visible in twilight hours and generally still quite observable, manageable. But as the solar elongation drops below about 45 degrees, things start to get dicey. The object is too close to the sun in the sky. You can only see it in a narrow window just before sunrise or just after sunset, and once the elongation drops below about 20 degrees, observation from the ground becomes effectively impossible. The object is lost in the glare. Now here's the problem. Objects on orbits that pass close to the sun, which is exactly what rock comets do, spend most of their time at low solar elongations. Think about it. If your perihelion is 0.22 astronomical units, your orbit dips way inside Earth's, and for most of the portion of your orbit that's closest to us, you're on the far side of the sun, or you're appearing very near the sun from our perspective. You're in the part of the sky that gets blotted out every day by solar glare. You're, for all practical purposes, hiding in plain sight. This isn't a temporary problem that will resolve as the object moves. It's a structural feature of how the orbit works. Objects with low perihelia are, by the math of their own orbital geometry, preferentially located in our sunward blind zone. This is why rock comets were relatively recently recognized as a class, even though many of them have probably existed for millions of years. We were literally unable to look where they spent most of their time. I want you to hold in your mind an image of what this looks like. Picture Earth orbiting the sun. Now picture a cone extending from your position outward, defining the region of sky you can actually observe at night. That cone is wide, but it doesn't reach everything. There's a wedge on the other side, the wedge pointing toward the sun, that you cannot see into. That wedge is vast. It contains a significant fraction of the volume where near-Earth objects spend their time, and most importantly, it contains the entire orbital region that objects with low perihelia pass through on their way in and out. This is the observational blind region. It is permanent. It is not going to go away. And it is not a small blind spot. It's a fundamental hole in our coverage of the inner solar system, and until recently, there was nothing we could do about it. NASA has acknowledged this for a long time. The detection gap for objects in sunward orbits is one of the known limitations of current planetary defense surveys. The population of near-Earth objects that has been catalogued is biased toward objects that spend most of their time in parts of the sky we can actually see. Objects that live primarily in the sunward region are systematically undersampled in our catalogues. They are, by the nature of our instruments, invisible to us, which means that the size of the unseen population, for objects in these kinds of orbits could be significantly larger than the size of the seen population. We don't know how much larger because you can't measure what you can't detect. But estimates from modelling studies suggest that the sunward blind zone could contain a substantial fraction of the total near-Earth population, possibly dozens or hundreds of objects in the rock comet class alone. And this is where M 2026 A1 becomes really important, because it's not just a new meteor stream, it's proof that the blind spot is populated. It's evidence that the unseen population isn't just a statistical abstraction, it contains actual, real, active objects that are influencing Earth's environment right now. The hidden parent of this stream has been in that blind zone for who knows how long, shedding material on every perihelion passage, slowly building up a debris trail that Earth only just this spring passed through. If one such object exists and we've detected it indirectly, statistical reasoning says many more should exist. This isn't a unique case. It's almost certainly a representative case. The question isn't whether the blind zone contains objects. It does. The question is how many and how active, and whether any of them are on orbits that might eventually produce something more dramatic than a meteor stream. This is why NEO Surveyor matters. NEO Surveyor is a NASA mission designed specifically to address the sunward detection gap. The spacecraft is being built to operate in the infrared part of the spectrum, which is important because infrared detection doesn't depend on reflected sunlight the way visible light detection does. Instead, it picks up the thermal emission of objects themselves. Every object warmer than absolute zero radiates in the infrared, and from the right vantage point in the right orbit, away from Earth's warm atmosphere, you can detect that thermal emission, even from objects near the Sun. The planned deployment is at the Earth-Sun Lagrange Point 1, known as L1. L1 sits between Earth and the Sun, about 1.5 million kilometers inward from us. From that position, a spacecraft looking outward can survey the inner solar system, including the sunward blind zone that ground-based telescopes can't reach. It's the observational equivalent of stepping out of a room where the light is directly in your eyes, so you can finally see what was hidden by the glare. The problem is that NEO Surveyor hasn't launched yet. The current schedule puts the launch no earlier than 2027. That means for at least another year, possibly longer depending on schedule slippage, the blind spot stays blind. We are currently reconstructing the unseen population indirectly, through meteor stream analysis like Flybys, because we don't yet have the instruments to see the sources themselves. Think about where that puts us. Our best current understanding of what's in the sunward zone comes not from looking at it, but from looking at what it sends us. We're like forensic investigators working a case where we can examine the evidence, but not the scene. We can see the debris, we can measure the meteors, we can calculate the orbits, we can infer the properties of the parent, but we cannot see it. Not yet. Possibly not for years. And in the meantime, the blind zone keeps delivering. Material keeps arriving. Streams keep being built up. Parents keep shedding. And Earth keeps moving through the orbits of objects we will not see until we launch a telescope that can look at the Sun without flinching. Which brings us to a question that Flybys' paper addressed, almost in passing, but that turns out to be enormously important. Because before this story was about rock comets shedding material slowly over centuries, a lot of people, including some scientists, suspected a very different kind of mechanism might be at work. A more dramatic one. A more sudden one. One that could have, in theory, produced a stream this significant in a much shorter time. That mechanism was tidal disruption. And when Flybys went looking for it, he didn't find it. Part 6. What the paper didn't find. One of the most important things a scientific paper can do is tell you what isn't there. We tend to focus on discoveries, on confirmations, on the things that show up in the data. But in science, a negative result, the finding that something expected didn't happen, can be just as important as a positive one. And Flybys' paper includes a significant negative result that hasn't gotten nearly the attention it deserves, because it directly refutes one of the most popular narratives circulating online about the meteor stream. That narrative goes like this. Some very large asteroid, possibly in a decaying orbit, passed close enough to the Sun or to a planet to be ripped apart by gravitational forces, producing a massive cloud of debris that Earth is now passing through. This is called tidal disruption. It's the same process that tore comet Shoemaker-Levy 9 into fragments before it slammed into Jupiter in 1994. The parent body gets too close to a gravitational well, the tidal forces exceed the object's internal cohesion, and the object literally comes apart in seconds. Tidal disruption, if it happened, would leave a specific signature in a meteor stream. You'd expect to see a cluster of orbits very tightly packed, because all the fragments would have started their independent journeys from nearly the same point in space at nearly the same moment. The orbital parameters would be almost identical, with only small variations introduced by the breakup event itself. Over time, those orbits would diverge, but in the short term you'd see a sharp, concentrated cluster rather than a diffuse, broadly distributed stream. Schober went looking for exactly this signature. The paper includes a dedicated analysis specifically designed to detect tidal disruption events in the meteor data. The statistical methods used were rigorous, the dataset was large, and the parameter space examined was comprehensive. If tidal disruption had happened recently enough to be contributing significantly to the observed fireball activity, the analysis would have found it. It didn't find it. The result was a null finding, with a quantitative upper limit. The contribution of any tidal disruption event to the observed population was calculated as less than or equal to 2.3 times 10 to the negative fourth. In plain language, that means if tidal disruption is contributing at all, it's contributing less than about 0.02% of the observed meteors. That's essentially zero. For all practical purposes, the data rules out tidal disruption as the source of what Earth has been experiencing. This is a big deal, and here's why. A lot of the viral narratives circulating right now are built on the assumption that something catastrophic happened, that an asteroid broke apart, that a sudden event spawned a cloud, that we're watching the aftermath of a cosmic collision play out in real time. Those narratives are compelling because they make the story feel dramatic and urgent, but the data doesn't support them. The data supports the exact opposite scenario, which is the slow, steady rock-comet mechanism we've been discussing. Slow thermal breakdown versus sudden fragmentation. Those are two very different stories about how debris enters Earth's orbital path. One implies an object that's been quietly producing a trail for thousands of years. The other implies an object that came apart recently and violently. The evidence, as of Schober's paper, points overwhelmingly to the first scenario, and that means the narratives spreading online about catastrophic breakups are, at best, misinformed and, at worst, deliberately sensationalized. This matters because it refines our understanding of what's actually happening. We now know, with good confidence, that the invisible asteroid shaping our recent sky is not a freshly shattered object. It's a rock comet doing what rock comets do on a timescale that predates human civilization. It's not a fresh event, it's an old one that we're only now detecting, and that's the callback point I want to make before we move on. The only confirmed mechanism producing the debris Earth has been moving through is the slow, patient disintegration of a single invisible rock comet. That's the mechanism Schober's data supports. It means that unseen objects, operating on geological timescales, are actively shaping Earth's meteoroid environment right now, and we are only just beginning to detect their signatures. The hidden parent is not an emergency, it's a revelation, and the revelation is about the observational gap, not about any new danger. Which brings us finally to what Earth has actually been experiencing in its sky for the past several weeks, because the story of M2026 A1 is one thread, the story of the fireball anomaly is another, and the question of whether those two threads are the same thread is the question we're going to spend the next several parts answering. Part 7. The 4.5 Sigma Signal. The American Meteor Society has been keeping records on fireball activity for decades. They collect eyewitness reports, they cross-reference with instrument data, they track physical meteorite recoveries, and they maintain one of the most comprehensive datasets in the world for what's happening in Earth's upper atmosphere. Most of the time, that dataset looks like background. Events rise and fall with the rhythm of known meteor showers. Fireball counts tick up during the Perseids, the Geminids, the Leonids, and then drop back to baseline. Occasionally you'll see a spike tied to a specific event, but over long timescales, the numbers are remarkably stable, and deviations from the norm are usually small. In the first quarter of 2026, something changed. Starting in March, the AMS began logging a significant increase in fireball reports. Not just a small uptick, a substantial, statistically meaningful surge. By the end of Q1, they had done the math, and they classified the anomaly at 4.5 sigma. If you're not familiar with sigma notation, 4.5 sigma means that the probability of this happening by random chance, without any underlying cause, is roughly 1 in 200,000. That's not a fluke. That's a signal. That's something happening. What exactly was happening? Several things, all at once. The first was a doubling of activity from the Anthelian source. The Anthelian is a region of the sky, centered roughly on the point directly opposite the Sun from Earth's perspective, where a significant amount of meteor activity naturally concentrates due to Earth's orbital motion. Think of it as the headwind region of our orbit, the direction Earth is effectively moving into as it goes around the Sun. Meteors coming from the Anthelian tend to be slower than average, because they're on orbits that Earth is catching up to rather than colliding with head-on. Doubling of Anthelian activity means that whatever was feeding that region was doing so at twice the normal rate. The second component was an increase in high declination fireballs. Declination, in astronomical terms, is the celestial equivalent of latitude. High declination means events happening in parts of the sky far from the equator. A surge in high declination fireballs points to a source whose orbit has significant inclination, meaning it's tilted relative to the plane of the solar system. Most meteor streams have modest inclinations. High declination anomalies suggest either a more tilted source or contributions from multiple sources, or both. The third component was the most striking. The AMS logged 1,693 long-duration sightings during the anomaly window. Long duration, in this context, means meteors that burn for extended periods as they cross the sky, as opposed to the brief flashes that make up most meteor activity. Long-duration events are rare. They typically require meteoroids of a certain size and composition, entering at specific velocities at specific angles. They're the kind of thing that makes people stop what they're doing and run outside. And 1,693 of them in a single quarter is 2.5 times the previous record. Beyond the visual data, there were sonic boom confirmations. Sonic booms happen when a meteoroid is large enough and entering fast enough to create a shockwave as it compresses the air in front of it. Those booms are detectable by infrasound networks, by seismometers, and sometimes just by people's ears. The AMS cross-referenced visual sightings with acoustic data and confirmed multiple events where both channels registered the same meteor. That's important because it rules out reporting bias. If people were just looking up more because of something going viral online, they'd be reporting more visual events, but the acoustic data wouldn't corroborate them. The fact that instruments were catching the same events tells you the events were real. And then there were the meteorites. 2 confirmed Howardite Eucrit diogenite, or HED. Meteorite falls in a 9-day window. HED meteorites are a specific class of stony meteorite believed to originate from the asteroid Vesta. Recovering 2 of them in such a short time frame is unusual on its own, regardless of any other context. Physical meteorite recovery is the ultimate confirmation that something is happening. You can't report a meteorite into existence. Either the rock is there or it isn't, and 2 of them were. Now, skeptics of the anomaly had a ready explanation. They pointed out that 2026 has seen a significant rise in AI-generated content and social media amplification of sky events. Maybe people were just reporting more because the algorithm was feeding them more content about the sky. Maybe the anomaly was an artifact of modern attention rather than actual activity. It's a reasonable hypothesis, and if visual reports were the only thing that changed, it would be worth taking seriously. But the visual reports weren't the only thing that changed. The acoustic data changed, the seismic data changed, the infrasound detections changed, and most importantly, physical rocks fell out of the sky. You cannot fake an HED meteorite. You cannot generate a sonic boom with a TikTok. The multi-channel consistency of the anomaly, the fact that visual, acoustic, and recovery data all pointed in the same direction, made the reporting bias explanation inadequate. Something was actually happening in the near-Earth environment. More material was entering the atmosphere than usual. Some of it was making it to the ground, some of it was big enough to make noise, and the pattern couldn't be explained by any of the usual known meteor showers active in that time period, which is where it all starts to connect back to the hidden parent of 2026A1. Because if there was a source of additional material in Earth's orbital path, and that source was unidentified, and a peer-reviewed paper 5 days ago just identified a new meteor stream from an unseen parent in that exact window, you have to ask whether those two things might be the same thing, not coincidentally happening at once, but the same underlying system, becoming visible from two different angles at once, which is exactly what you'd expect if you were watching an unseen object finally reveal itself through its effects. The AMS anomaly is the first half of the evidence, Schober's paper is the second half, and the question of whether they line up, whether the timing and the geometry actually match, is where this story either resolves into a coherent picture or fractures into a handful of unrelated observations. That's what we're going to look at next, and what we find is going to be interesting. Part 8. The overlap that changes everything. Here's where the story either comes together or falls apart, because if Schober's M2026A1 stream and the AMS fireball anomaly are actually connected, the evidence for that connection has to show up in the timeline, in the geometry, and in the physical properties of the observed meteors. Let's walk through each one. The timeline first. Schober's analysis identified the active window for the M2026A1 stream as running from roughly March 16th to April 7th. That's a 3-week window, which is typical for meteor streams tied to near-Earth objects. Earth enters the debris trail, moves through it for a period determined by the stream's width and our orbital velocity, and then exits out the other side. The AMS anomaly, meanwhile, peaked in late March and continued into early April. When you overlay the two windows, they're not just close. They're almost the same window. The overlap is approximately 3 weeks, which means the period during which Earth was passing through the M2026A1 stream is essentially the period during which the fireball anomaly was at its most intense. That alignment on its own would be suspicious but not conclusive. Two events happening in the same window could be coincidence. To move beyond coincidence, you need to check the geometry. The geometry checks out too. The radiant of the M2026A1 stream, the direction in the sky the meteors appear to come from, falls within the region where anthelion source activity concentrates. Remember, the anthelion is the part of the sky roughly opposite the Sun, in the direction Earth is moving into as it orbits. Streams whose parent bodies have certain orbital configurations produce meteors that radiate from that region. M2026. A1's geometry places its radiant in that general area, which matches the doubling of anthelion activity the AMS logged. That's two independent observations pointing to the same part of the sky. That's not a coincidence. That's a match. The physical properties also line up. The meteors associated with M2026A1 have compositional properties consistent with moderately fragile meteoroids. They're not ultra-dense metal-rich particles. They're not ice-dominated cometary grains. They're something in between, consistent with material shed from a rock comet that's been thermally processed near perihelion. And when those kinds of particles enter the atmosphere, they tend to produce bright, slow fireballs. Bright because they have enough material to generate significant light. Slow because their orbital velocities, being similar to Earth's, mean they're not coming in at the kind of hypersonic speeds that characterize high-energy meteors. Bright and slow. That's exactly the kind of fireball the AMS was reporting in elevated numbers during the anomaly window. The long-duration sightings, the ones that made people run outside to see what was happening, were disproportionately this type of event. The physical signature of what was coming down matches what the M2026A1 stream would be expected to produce. When you stack all of that together, what you have is the first plausible physical mechanism for the anomaly that the AMS has been flagging since March. The stream, the radiant, the timing, and the meteor properties all line up. This isn't speculation. This is a confirmed meteor stream, identified through a peer-reviewed paper, whose active window, geometry, and physical signature match the characteristics of an anomaly that had no explanation for almost a month. Now, I want to be careful here, because the science community tends to be cautious about causation claims, and for good reason. Correlation isn't causation, even when the correlation is strong. Just because two things line up in time, in space, and in physical signature doesn't mean they're directly linked. It's possible that M2026A1 contributed to the anomaly without being its sole cause. It's possible that there were multiple sources operating simultaneously, and the stream was just one of them. And in fact, there are reasons to think that's exactly what's happening. The HED meteorite falls, for example, don't fit the M2026A1 profile. HED meteorites come from Vesta, which is a main belt asteroid, not a sunward rock comet. The two HED falls during the anomaly window are almost certainly unrelated to the meteor stream. They're a separate signal, possibly just statistical variation in the background rate of meteorite falls, or possibly indicative of something else entirely. The high declination fireballs are also only partially explained. Some of them could be from M2026A1, depending on exactly where in the stream they entered the atmosphere, but the high inclination portion of the anomaly might require contributions from other sources, possibly including streams that haven't been identified yet. So what we have is a partial explanation. M2026A1 accounts for a significant portion of what the AMS logged. It doesn't account for all of it. And that gap between what the stream can explain and what the anomaly actually contained is one of the most interesting parts of the whole story. The framework I want to offer you is this. What we're looking at might not be a single phenomenon. It might be a compound anomaly, meaning multiple separate events overlapping in time to produce a combined signal that looks like one thing but is actually several. That's a harder hypothesis to test, and it's a harder hypothesis to explain to the public, because it requires holding multiple partial explanations in mind at once. But it might be the most accurate characterization of what's actually happening. If you run the probability calculation on independent events aligning this way, it gets interesting. The chance of an unrelated meteor stream being discovered in the exact window of an unexplained fireball surge with matching geometry and physical signatures is very low. It's not impossible, but it's low. The chance of that happening at the same time two unrelated asteroids fly by us within 24 hours, and all of this converging into a single week, is even lower. This doesn't mean the events are causally linked in some cosmic master plan. It does mean that something about Earth's current orbital environment is producing multiple signals at once, and those signals are being noticed. Scientific caution requires us to not overclaim. We don't have confirmed causation, we have strong correlation, we have partial explanation, we have a framework where one peer-reviewed discovery matches a significant portion, but not all, of what an independent dataset recorded. That's the first time any of this has happened. For weeks, the AMS anomaly was just an anomaly. Now, for the first time, there's a physical mechanism that could at least partially account for it. And that mechanism was validated through peer review 5 days ago. This is what I want you to take away from this section. Theory and observation have met in the middle. Schober's calculated stream, derived from orbital mechanics and meteor clustering, matches what the AMS was seeing with their ground-based cameras and their network of reporting observers. That's not a small thing. That's the kind of convergence that science lives for. That's the moment when the model and the data start to describe the same object. And if this is only one component of a larger system, if the compound anomaly hypothesis is right, then what we're witnessing is the first signal of a near-Earth environment that contains more unseen sources than we currently understand, which, if you've been paying attention, is exactly the central thread of this entire story. The hidden is becoming visible through its effects, and the effects are more than one. Part 9. Independent signals. I want to walk through a couple of additional data points that, while not decisive on their own, contribute to the overall picture of what's been happening in Earth's orbital neighbourhood over the last several weeks. These signals are independent from the AMS fireball data and from the M2026A1 stream paper, which makes them interesting. When multiple unrelated observational channels start pointing in the same general direction, you have to take that seriously, even when each channel on its own is noisy. In science, independence is leverage. A single data set, no matter how good, can always be wrong for reasons nobody has thought of yet. Two data sets, pulled from different instruments, in different locations, using different methods, are much harder to dismiss. 3 or 4 becomes almost impossible to wave away as coincidence or artifact. So when we're evaluating whether something is actually happening in the near-Earth environment, we don't just ask whether any one channel is lighting up. We ask whether multiple channels are lighting up at once, and right now, they are. The first signal came from the Moon. During the Artemis 2 mission's eclipse observation window, lunar observers recorded 6 visible impact flashes on the Moon's surface. Impact flashes happen when meteoroids hit the lunar regolith, which has no atmosphere to slow them down, and release their kinetic energy as brief bursts of light. These flashes are tiny, lasting a fraction of a second, but with the right instruments they're perfectly detectable, and the data on them is some of the cleanest we have for characterizing what's actually present in the near-Earth environment. There's no atmospheric interference to correct for, There's no eyewitness bias to filter out. There's no reporting lag. A meteoroid hits, light comes off, the camera catches it. Simple physics, simple observation, straightforward interpretation. 6 impacts during a focused observation window is more than baseline rates would predict. It's not so far above baseline as to be impossible randomly, but it's on the high end of what you'd expect, and that matters when you're looking at it alongside everything else. Now, the Moon is in the same orbital neighbourhood as Earth. That's an obvious statement, but its implications are worth spelling out. The Moon orbits Earth at an average distance of about 239,000 miles, which means on cosmic scales, Earth and the Moon are essentially in the same place. They share an orbital environment. They sweep through the same regions of space as our combined system orbits the Sun. If Earth is passing through a debris stream, the Moon is too, or at least near enough that some of the same material can be intercepting it. The geometry isn't perfect. Depending on where the Moon is in its orbit around Earth, it can be inside or outside the densest part of a debris trail. But in broad terms, what affects Earth affects the Moon, and vice versa. An uptick in lunar impact flashes during the same broad window as Earth's fireball anomaly is suggestive. It's independent of Earth-based reporting, which means it can't be explained by AI reporting inflation or social media hype. It's just flashes on the Moon, captured by professional instruments, showing something hitting the surface. And those instruments don't have a Twitter account. They don't chase headlines. They just record what happens. The spatial correlation between the lunar flashes and the M2026A1 stream isn't perfect. That's worth acknowledging, honestly, because the data doesn't quite lock the two phenomena together the way you might want it to if you were writing a movie. Some of the lunar impact geometry doesn't quite match the stream's radiant. The direction from which those meteoroids appear to have been coming, when you project their paths backward across the lunar surface, doesn't sit cleanly inside the region where M2026A1 should be depositing material, and the Moon's position relative to Earth during the observation window means not all of the impacts can be directly tied to the stream. Some of them might be from the stream, some of them might be from unrelated sources. Without more detailed trajectory analysis, we can't say with certainty which is which. But the general timing and the elevated rate fit into the broader picture of an unusually active period in the near-Earth environment. You wouldn't expect to see 6 impacts during a typical observation window. You did see 6. Something was happening. The exact fingerprint doesn't match perfectly, but the overall pattern of elevated activity is there, and it's there in a channel completely divorced from any of the reporting bias concerns that follow Earth-based data. The second independent signal, and this one is more of a caveat than a confirmation, involves the well-known issues with CNEOS fireball data. CNEOS is the Center for Near-Earth Object Studies, and they maintain a public database of fireball events detected by government sensors. These sensors are sensitive, they cover most of the planet, and they generate data that's available to researchers and to the general public. That database is enormously useful, and anyone studying fireball activity depends on it in one form or another. But it has known problems, particularly with coordinate accuracy. The sensors were originally designed for other purposes, and the process of converting raw detection data into precise fireball coordinates involves assumptions that don't always hold up. There was an event on March 25th where the CNEOS listed coordinates were off by roughly 1,800 miles from where the actual event occurred, based on cross-referencing with AMS eyewitness reports and local news coverage. That's not a rounding error, that's an entire continent's worth of difference. If you were trying to tie that specific event to a source region, or to match it with other instrumental data, the bad coordinates would send you chasing a phantom. This kind of coordinate error isn't malicious. Nobody at CNEOS is trying to mislead anyone. It's a known limitation of how the sensors work and how the data gets processed, and the community has understood it for years. But it means that any individual CNEOS detection has to be cross-verified before it can be used as evidence. You can't just pull a number from their database and treat it as gospel. You have to check it against the AMS, against NASA's other datasets, against local reports, and against any other instrumental confirmations available. If the numbers all line up, you can trust the event. If they don't, you have to figure out which one is wrong. That process takes time, and it requires judgment, and it means that the public-facing story is always a little behind the actual state of the data. Because the first version of any fireball report is provisional, the confirmed version might not land for days or weeks after the cross-verification is done. During the anomaly window, A significant amount of the work being done by independent researchers was exactly this kind of cross-verification. Pulling CNEOS events, checking them against AMS reports, looking for news coverage of corresponding ground-level observations, checking local infrasound data where it was available, and building a consolidated picture of what actually happened. Some events were confirmed quickly. Others required digging through regional news archives in multiple languages to find corroboration. A few events turned out to be errors and were quietly set aside. Others turned out to be real and significant, but with properties different from what the initial data had suggested. That process is slow, and it's imperfect, and it's the kind of painstaking work that never makes the news because it doesn't generate headlines. But it's exactly the kind of work that separates a plausible story from a verified one, and it means that our current understanding of the anomaly is still being refined as new data comes in and old data gets corrected. What this tells you is that data uncertainty is a real limiting factor. We don't have a crystal clear picture of exactly what happened in Earth's atmosphere during March and early April. Anyone who tells you they do is either working with information that isn't public or overstating their certainty. We have a picture assembled from multiple partially reliable sources, cross-referenced as much as possible, and that picture is strong enough to conclude that something unusual occurred, but not strong enough to pin down every detail. That's an uncomfortable position to be in, because we like stories with clean resolutions and precise numbers. We like being able to say exactly what happened, when, and why. Science doesn't always deliver that, especially not in the first few weeks after a phenomenon is identified. The precision comes later, after the data is cleaned, verified, reprocessed, and compared across multiple channels. What we have right now is the first draft. The final version is going to look more defensible, and it's also probably going to look a little different from what we're seeing today. And here's the part I want to emphasize. Even with imperfect data, even with coordinate errors, even with the need for painstaking cross-verification, the overall signal still points toward an active, partially unseen meteoroid environment. That's not a conclusion that depends on any single data point being perfect. It's a conclusion that emerges from multiple channels, each of them flawed in its own way, all of them pointing in the same general direction. The lunar flashes suggest elevated activity. The AMS visual reports suggest elevated activity. The acoustic confirmations suggest elevated activity. The meteorite recoveries suggest elevated activity. No one of these is decisive, but together they paint a picture that's hard to explain with any single trivial cause. Something happened. Something is still in some form happening, and the question is what, and why, and how much of it we can actually map. The hidden parent of M2026A1 isn't the only unseen contributor, it's just the first one we've identified. That's worth sitting with, because it reframes what we just witnessed. We didn't discover a unique, one-of-a-kind object. We discovered, with high confidence, that at least one such object exists in the sunward blind zone, feeding a confirmed meteor stream into our orbital path. If one exists, statistical reasoning says others do too. The compound nature of the anomaly suggests there are likely others still waiting to be caught, and the observational gaps that made the hidden parent invisible are the same gaps that might be hiding additional sources right now, tonight, as you're watching this. The blind zone didn't close when Schober's paper got published. It's still there. It's still a blind zone. It's still catching parents we haven't seen yet. Which is why the next part of this story matters. Because while scientists have been carefully working through the data, building models, cross-verifying sources, running statistical tests, and publishing peer-reviewed papers, the internet has been moving much faster, and the story it's been telling doesn't always match the story the data tells. The scientific process is methodical. The viral process is explosive. One takes months to get something right. The other takes minutes to get something mostly wrong. And the gap between viral narrative and scientific reality is where a lot of the public confusion lives. That gap is worth examining, because it tells us something important about how we collectively make sense of discoveries like this one, and about how the shape of a real story gets distorted when it leaves the journal and enters the feed. Part 10. The viral narrative versus scientific reality. Scroll through any social media platform right now, and you can find versions of this story that sound very different from what we've been discussing. The viral framing goes something like this. Earth is flying through a cloud of asteroid debris. The fireballs are just the beginning. A hidden object is breaking apart. Something is coming. The government isn't telling us. The skies are about to get worse. You've seen the posts. You've seen the videos. You've probably seen at least one of them in the last 24 hours if you've opened any of the major platforms. The thumbnails are aggressive. The captions are dramatic. The comment sections are full of people asking whether they should be preparing for something, whether they should be stocking up on supplies, whether they should be looking at the sky differently tonight than they did last week. Some of that is loosely grounded in real events. We are, it's true, passing through the debris trail of an object that was previously unseen. Fireball activity has genuinely been elevated, and there is a peer-reviewed paper confirming the existence of a new meteor stream. Those facts by themselves provide the seed material that the viral narratives grow from, which is important to acknowledge, because if the underlying story were completely fake, it would be easier to dismiss the viral versions. The problem is that the underlying story is real. It's just been reshaped, as it travelled, into something that carries a different weight than the original version did. What happens in the space between the facts and the narrative is a kind of compression, where the timeline gets crushed, the scale gets amplified, and the tone shifts from careful observation to urgent warning. And once that compression happens, it's very difficult to uncompress. You can't easily put nuance back into a story that's already been flattened for the algorithm. The compression of timescales is the biggest misunderstanding, and I think it's worth slowing down on this one because if you understand this one thing, you'll have the tools to interpret almost any piece of astronomy news that comes at you in the future. When we say Earth is passing through a debris trail, what we actually mean is that our orbital path is intersecting a region where dust and small particles have accumulated over thousands of years. Thousands, possibly tens of thousands. The hidden parent of M2026A1 has been shedding material for longer than human civilization has existed, and the stream we're currently moving through is the sum total of all the ancient leaking concentrated along a specific orbital path. That intersection lasts weeks, and during those weeks, the density of material is a tiny, tiny amount above the background level of space. If you could somehow scoop up a cubic kilometre of space inside the densest part of the stream, you would find something like a handful of sand scattered across a volume the size of a small city. That's what it actually looks like. That's the density we're talking about. It's not a cloud, it's not a wall of rock, it's a subtle statistical increase in the number of small particles per unit volume, measurable only because we have sensitive enough instruments to detect the difference. The particles themselves are small, mostly the size of sand grains, sometimes larger, but overwhelmingly too small to cause any damage beyond a bright streak in the sky. Your roof is safe, your car is safe, your satellites are safe, the International Space Station is safe, aircraft are safe. Nothing about this stream poses any meaningful threat to any physical infrastructure. The scenario of Earth flying through a cloud implies something dense and dangerous, something you'd want to hunker down for, something that might make the news for reasons beyond its scientific novelty. The reality is something diffuse and largely invisible, whose main effect is a modest increase in fireball activity that the AMS can measure statistically, but that individual observers might not even notice night to night. If you went outside last week and looked up, you probably saw exactly the same sky you always see. You might have seen a few more bright meteors than usual if you were lucky. You did not see a cloud of anything. You could not have seen a cloud of anything. There was no cloud. The geological versus human timescale distinction matters here, and this is one of the places where intuition really leads people astray. Human brains evolved to track events on scales of days, weeks, years. Our news cycles run on hours. Our attention spans run on seconds. Geology runs on millions of years. Orbital mechanics runs on thousands. When you try to collapse geological time into human time, you end up with stories that feel wrong to a scientist even when every individual word in them is technically defensible. Rock comet activity, the kind that produces M2026A1, operates on geological timescales. The hidden parent has probably been shedding material for thousands of years, possibly tens of thousands. The stream we're currently passing through represents the cumulative output of all those years, concentrated along the orbit of the parent. When we encounter it, we're not encountering anything new. We're encountering the accumulated history of a process that started long before humans existed. The debris was already there when the pyramids were built. It was already there when the last ice age ended. It was already there when our species started using language. And yet, when it shows up in a headline, it sounds like something that started last month. framing that as something suddenly happening, as something urgent, as something we should be worried about, confuses the timeline. It takes a slow, patient, geologically gradual phenomenon and compresses it into a headline that feels immediate. That compression is what creates the alarm, and it's what makes the viral version of this story feel so different from the scientific version. The physics didn't change, the observation didn't change, the actual material in the actual stream didn't change. What changed is the frame around the information, and the frame is doing most of the emotional work. Part of why this happens is that narratives spread faster than peer-reviewed nuance. Science, by its nature, is slow. It's careful. It qualifies everything. A good scientific statement is full of hedging language, acknowledges uncertainty, and makes explicit the limits of what can be concluded. You read a planetary science paper and you'll find words like probable, possible, consistent with, suggestive of, tentatively identified, statistically significant, but not decisive. Scientists talk this way because they have to. Overreach destroys careers. Claims that don't hold up get cited as cautionary examples for the rest of the field's lifetime. The incentives in science are, on balance, incentives toward restraint. Social media, by contrast, rewards clarity, urgency, and emotional hook. The phrase Earth is passing through a debris stream produced by a slow thermal disintegration process over a geological timescale does not perform well on any algorithm. Nobody is sharing that. Nobody is commenting on that. Nobody is stitching that into a video. The phrase Earth is flying through an asteroid cloud performs extremely well. Both phrases can, in some sense, be describing the same physical situation, but they communicate very different things, and the platforms will always amplify the second one over the first one. Not because the platforms are malicious, but because that's what the attention economy does to information. Urgency wins, nuance loses. That's the shape of the environment we're all operating in, and it's the reason the viral version of every science story drifts away from the scientific version over time. There's an overlap between truth and exaggeration that makes this particularly tricky to untangle. The viral narratives aren't entirely wrong. I want to be really clear about that, because it would be easy to paint them as pure misinformation, and that framing would itself be inaccurate. They're compressed and exaggerated, but they're grounded in real events. The meteor stream exists. The fireball anomaly is real. The detection of the hidden parent through its effects is a genuine scientific first. The issue isn't that the viral version is pure fiction, it's that the viral version is true data plus inaccurate framing, and the framing is what changes the meaning. That makes it harder to debunk because every time you try to push back on a specific claim, the response can be, well, but there really is an asteroid, there really are fireballs, there really is a paper, and all of that is correct. The problem isn't in the individual facts, the problem is in the emotional wrapper around them. Precise language matters when you're trying to communicate something like this, and I want to give you a few concrete examples so you can see what the difference actually looks like in practice. Saying Earth is passing through a debris stream is accurate. Saying Earth is flying through a cloud of asteroid debris is technically close to accurate, but implies a density and danger level that doesn't match reality. Saying a hidden asteroid has been detected through its meteor stream is accurate. Saying an invisible asteroid is attacking Earth is not. Saying fireball activity has been elevated is accurate. Saying the skies are erupting is not. Saying we're passing through material that's been accumulating for thousands of years is accurate. Saying something is breaking apart right now is not. The words you choose shape the perception of what's actually happening, and small differences in word choice can produce enormous differences in how people feel about the story. This is why careful writers and careful scientists fight so hard over specific phrases. It's not pedantry. It's recognition that language is the interface between reality and perception, and when the interface is wrong, the perception drifts from the reality in ways that are hard to correct after the fact. I want to briefly address the more extreme interpretations that sometimes show up in these conversations, because they're going to show up in your feed whether I mention them or not, and I'd rather you hear the rebuttal from me than encounter the claim without context. The Nibiru and Nemesis type theories, which posit the existence of a hidden planet-sized body on an eccentric orbit that periodically threatens Earth. Those theories have been circulating for decades. They predate this current story by a long way. They've been attached to every significant astronomical event in the last 20 years, from specific alignments of the planets to solar maximum cycles to spikes in earthquake activity. And they don't apply here. They don't apply because the physics doesn't work. A planet-sized body on a periodic orbit that brings it close to Earth would, by necessity, have gravitational effects on the rest of the solar system. It would perturb the orbits of the outer planets. It would be detectable in long-term astronomical records. It would show up in gravitational models. It isn't in any of those records. The absence of evidence is strong evidence of absence, when the expected effects would be so large that they couldn't be missed. If a body that size were there, we would know, not because a government agency would have to admit it, but because the math of the solar system would not close without it, and the math closes just fine. From 2026. A1's hidden parent is not a planet, it's an asteroid. Probably small, probably rocky, probably similar in size to other known near-Earth objects, and definitely nothing remotely like a second body in the solar system. It's hidden in the sense that it's in our observational blind zone, but it's not hidden in the sense of being supernaturally undetectable. Once NEO surveyor launches, once we have infrared coverage of the sunward region, it will almost certainly be one of the first objects that instrument catches. We'll get an image, we'll get an orbit, we'll probably get a spectrum. The mystery, such as it is about current instrumentation, not about the fundamental observability of the object. This isn't a conspiracy, it's a gap in our capabilities, and that gap is being actively addressed by a mission that's already well into development. The callback here is that the viral narratives arise exactly because we have real, but incomplete information about unseen objects. The data is real, the gap is real, the story is real. But when real and incomplete information enters public discourse without the scientific context needed to interpret it, it gets compressed into something that feels more dramatic than the reality actually is. That's not the public's fault. That's not the scientists' fault. It's just what happens when a genuinely strange discovery tries to cross from a peer-reviewed journal into a comment section. The information has to change shape to survive the trip. And in changing shape, it loses some of what made it accurate in the first place. The scientific reality is stranger, and in its own way, more interesting than the viral version. We have in fact confirmed the existence of an asteroid through its effects alone. We have in fact identified a new class of active near-Earth object. We have in fact documented an unprecedented fireball anomaly with multi-channel confirmation. Those facts, told carefully, are more than enough to make this a legitimately historic moment in observational astronomy. The story doesn't need to be inflated to be remarkable. It's already remarkable. It just requires being told honestly. And the honest version, as we've been working through it, is about a blind spot in our vision of the sky, a population of objects that lives inside that blind spot, and the first clear signal that population has finally given us that it's there. That's the actual story. That's what this week was really about. The viral version is loud. The real version is quieter and weirder, and ultimately much more interesting once you sit with it long enough to feel the shape of it. Part 11. 4 competing interpretations. Let me lay out the landscape of interpretation honestly, because the truth is that right now, today, as I'm recording this, scientists don't have a unified answer to what's actually happening in Earth's orbital environment. There are multiple ways to interpret the convergence of the past several weeks, and each interpretation has evidence for it and evidence against it. I'm going to walk you through 4 of them, as clearly as I can, and let you weigh them yourself. The first interpretation is coincidence. Under this framing, the 2 asteroid flybys this weekend, Schober's meteor stream paper, the fireball anomaly, and the lunar impact flashes are all separate, unrelated events that happen to be occurring in roughly the same calendar window. Random alignment, statistical variation, humans seeing patterns in noise because we're wired to find patterns whether they exist or not. Coincidence has some things going for it. The 2 asteroid flybys really are unrelated to the meteor stream. They're not fragments of the hidden parent, they're not part of the M2026A1 debris, and their trajectories don't connect to the stream's geometry. Those are genuinely independent events. Planetary Defense Surveys do log sublunar flybys on a regular basis, and having 2 in a single 24-hour window, while notable, isn't statistically impossible. The fireball anomaly, at 4.5 sigma, is harder to dismiss as coincidence. That's not a random fluctuation level, that's a signal. But you could argue that the anomaly is real and the meteor stream is real, but the connection between them is less tight than it appears. The timing overlap could be chance. The geometric alignment could be partially misleading. Under the strictest interpretation of what counts as proof, coincidence is still technically possible. The weakness of coincidence as an explanation is the number of separate pieces that have to all independently occur in the same window. Two unrelated flybys, one independent stream discovery, one independent fireball surge, one independent set of lunar impact flashes. Calling all of that coincidence is mathematically possible, but starts to strain credibility. It's a position you can defend, but you have to keep defending it against an increasing pile of signals. The second interpretation, and the one I think is the most balanced given current evidence, is partial explanation. Under this framing, M2026A1 is real. It is feeding debris into Earth's orbital path, and it is responsible for a significant portion of the fireball anomaly. Specifically, the portion that matches the stream's radiant timing and meteoroid properties. But the stream does not explain everything that was observed. The HED meteorite falls, the high declination fireball surge, and possibly the lunar impact flashes have sources that aren't part of M2026A1. Partial explanation is scientifically conservative. It accepts the evidence that's strong, explains what can be explained, and acknowledges that other factors are likely contributing. It doesn't overreach, it doesn't claim more than the data supports, and it leaves room for future observations to refine our understanding. This is probably where most working planetary scientists would land if you asked them today. The strength of partial explanation is that it fits the data well without requiring heroic assumptions. The weakness is that it doesn't fully explain everything, which feels unsatisfying. We like stories with clean resolutions, and partial explanation doesn't offer one. It says, here's what we know, here's what we don't, and here's what we're still working on. The third interpretation is the one I find most intriguing, and I'll be upfront that it's the most speculative. It's the broader environmental shift hypothesis. Under this framing, what we're seeing isn't just one stream and one anomaly. We're seeing evidence that Earth's local meteoroid environment is changing, possibly in ways we don't fully understand, and the multiple signals we're logging are all symptoms of a larger shift. This interpretation draws on the fact that multiple independent signals are aligning. The stream, the fireballs, the lunar impacts, the elevated meteorite recovery rate, the fact that two undiscovered asteroids are flying past us in a single day. Any one of those on its own is within normal ranges. Collectively, they start to look like a pattern. And if that pattern is real, it suggests that the near-Earth environment right now is simply more active than baseline, possibly because multiple sources are contributing simultaneously, possibly because we've entered a period of higher overall meteoroid density for reasons we haven't fully worked out yet. This is speculative. It's not a claim you can test easily with current data. It might be right, it might be wrong, and honestly, the current observational capabilities aren't sufficient to distinguish between a genuine environmental shift and a temporary increase that falls within natural variability. But it's the kind of hypothesis that gets investigated by looking for additional signals over longer timescales. If Q2 of 2026 shows continued elevated activity, that starts to look more like a shift and less like a temporary anomaly. If Q2 drops back to baseline, the shift hypothesis weakens. The fourth interpretation is the null hypothesis. Nothing unusual is happening. Everything we're observing falls within normal variability, enhanced by modern detection capabilities and social media amplification. The fireball anomaly is the result of more cameras, more reporters, more AI-driven content, and better networks producing the illusion of a surge where, historically, there would have just been an unremarked normal quarter. The meteor stream is real but small, and its contribution to Earth's environment is negligible. The asteroid flybys are routine. The lunar impacts are within baseline. The compound anomaly isn't real. It's an artifact of the time we happen to be living in. The strength of the null hypothesis is that it doesn't require any new physics, any hidden processes, or any unusual circumstances. It just says our detection infrastructure has gotten dramatically better over the past decade, and we're finally seeing what was always there. Historical underreporting is a real phenomenon. The AMS acknowledges that their own data from 20 years ago isn't comparable to their current data because the networks have expanded so much. What used to go unreported now gets logged. The weakness of the null hypothesis is the physical evidence. You can explain visual report inflation with detection improvements. You can explain sonic boom data with better instruments. But you can't explain HED meteorite falls as a detection artifact. Those rocks are either on the ground or they aren't. 2 of them showed up in 9 days. Whether that's unusual in a statistical sense depends on baseline rates that are themselves uncertain, but it's at least a data point that's not easily explained away. Evaluating these 4 interpretations, I'd say the evidence points most strongly toward partial explanation. The coincidence hypothesis is getting harder to defend as more signals accumulate. The broader environmental shift hypothesis is interesting, but not currently testable with the rigor needed to confirm. The null hypothesis explains some things but not all. Partial explanation fits the most data with the fewest assumptions. But I want to emphasize something important. We don't have decisive evidence for any single interpretation. The current state of knowledge is genuinely uncertain, and anyone telling you they know for sure what's happening is either working with data you haven't seen or overstating their confidence. This is one of those moments in science where the question is newer than the answer, and the answer is going to take more data, more time, and more careful work to arrive at. What future data would actually tell us? AMSQ2 numbers will be important. If the fireball anomaly extends into Q2, that favours the environmental shift hypothesis or a compound anomaly model. If Q2 returns to baseline, the anomaly looks more like a localised event, possibly tied specifically to the M2026 A1 stream window. Additional meteor stream discoveries in the coming months, if they emerge from the global network data, would suggest more hidden parents and support the broader shift hypothesis. NEO Surveyor, once it launches and begins operations, will be the ultimate arbiter of the sunward blind zone question. If it discovers a population of rock comets in the size range consistent with what modelling predicts, that confirms the blind zone is populated and validates the inference-based detection approach that Schober used. If the population turns out to be smaller than expected, that changes the picture significantly. The scientific process here is going to play out over years. We're at the beginning of this question, not the end, and the answer isn't going to come from a single observation or a single paper. It's going to come from the slow accumulation of data, the testing of competing hypotheses, and the gradual refinement of our understanding of what's actually in the near-Earth environment and how it's evolving. What's new, what's significant about this specific moment, is that we have, for the first time, a testable hypothesis connecting a peer-reviewed discovery to an observational anomaly. That's the milestone. Not that we know the answer, but that, for the first time, the question has been framed with enough precision that it can actually be answered. Part 12, the real question. Let me bring this back around to where we started, because if you've stayed with me through this entire journey, you deserve to have the pieces assembled into a single picture. And the picture, once you see it whole, is different from any of the headlines that have been circulating over the past week. The convergence is what makes this moment significant. 2 asteroid flybys within 24 hours, one of the closest back-to-back pair we've logged in recent memory. A peer-reviewed paper identifying a previously unknown meteor stream whose parent body has never been directly observed. A 4.5 Sigma fireball anomaly that's been building since March and whose cause was unknown until 5 days ago. A viral narrative racing ahead of the science, compressing geological timescales into urgent headlines, generating alarm that the actual data doesn't support. All of it stacked into the same week. None of these individual components is by itself earth-shaking. Flybys happen, papers get published, fireball counts fluctuate. Viral narratives emerge around every significant space news event. What's different about this moment is that when you put all the pieces together, they form a coherent story about detection limits, about what we can see, about what we can't, and about how much of the world around us operates in regions we haven't figured out how to observe yet. The invisible parent asteroid is the central discovery here, and I want to make sure that doesn't get lost. The 2 visible asteroids skimming past Earth tomorrow are the trigger, not the story. They're what put this week in the news cycle. They're what made people pay attention. But the actual substance of the discovery, the thing that will matter when this week is remembered, is the invisible third body, the one in the sun's glare, the one that has never been seen, the one whose existence we only know about because its debris has been burning up in our atmosphere. Reframing the flybys through this lens changes what they mean. They become, in a sense, a kind of cosmic coincidence that drew public attention to a moment that was already scientifically significant for reasons that had nothing to do with them. The flybys are not the story, they are the spotlight that illuminated the story. And under that spotlight, what we can actually see is a detection gap so fundamental to how we observe space that it has been hiding an entire category of active near-Earth objects for who knows how long. The detection gap is the core issue, and the implication of the gap is larger than any single object. If we've now confirmed, through inference, that at least one rock comet exists in the sunward blind zone, producing a significant meteor stream and affecting Earth's upper atmosphere, how many more are there? The mathematical answer, based on population modelling and what we know about the orbital distribution of near-Earth objects, is that there are probably many. Possibly dozens, possibly hundreds. The blind zone is not a small region of space, and the objects that orbit through it are exactly the kind of objects that leave debris trails. We are reconstructing a population we cannot directly observe. Every stream identified, every anomaly traced to an unseen parent, every fireball characterised and sourced is a data point in that reconstruction. M 2026. A1 is the first confirmed case. It will not be the last. What does this mean for planetary defence? More than you might think. Planetary defence is built on two assumptions. The first is that we can identify dangerous objects early enough to characterise them. The second is that our catalogues are comprehensive enough to have seen most of the larger threats. The sunward blind zone challenges both of these assumptions. Objects in that zone, by definition, are invisible to our current instruments. They can be on Earth-crossing orbits for decades without being detected, and while most of them are probably small enough not to pose an impact threat, some fraction of them might not be. We simply don't know, because we can't see them. The slow disintegration process of rock comets means that, on any given orbit, they're not a sudden threat. They don't catastrophically fall apart and create an impact hazard from nothing. They shed material gradually, over timescales that dwarf human experience. But the fact that we can't see them means that any characterization of individual objects, any ability to predict their behavior or rule out hazards, is impossible until we close the observational gap. NEO Surveyor will help, future missions will help more, but for now we're flying blind in one specific direction, and that blindness is starting to become visible through the anomalies we can measure. The fireball anomaly, to bring that thread back in, remains partially unexplained. M 2026. A1 accounts for a significant portion of it, but not all. The HED meteorites, the high declination events, the lunar impact flashes, the multi-channel nature of the surge suggest that there are additional contributors we haven't yet identified. Those contributors might be additional streams, they might be temporary enhancements from known sources, they might be statistical variations. We don't know yet. But the fact that we can't fully account for what Earth's upper atmosphere was doing for 3 weeks in March and April means the detection gap might be wider than just one hidden asteroid. The forward-looking questions are the interesting ones. How many similar streams exist, waiting to be identified in the global meteor network data? How many parent bodies remain undetected in the sunward blind zone? How much of Earth's routine meteoroid environment comes from sources we have never observed? These aren't rhetorical questions. They're questions that will be answered slowly over the coming years as more data accumulates, more analyses are run, and more instruments come online. We are at the beginning of this investigation, not the end. The role of future missions cannot be overstated. NEO Surveyor, when it launches in 2027, is going to rewrite a significant chunk of the near-Earth object catalogue. Objects that have been invisible for as long as we've been looking at the sky will suddenly become visible. Parent bodies of existing streams, which currently have to be inferred through analysis like Schober's, will get direct detection. New objects we haven't even suspected will show up in the first survey data. That's going to be an interesting moment, and it's close enough now that we can start to anticipate what it might reveal. In the meantime, we should be doing exactly what we're doing, continuing to analyse meteor network data, publishing peer-reviewed work on newly identified streams, cross-referencing fireball anomalies with emerging mechanisms, building up our understanding of the invisible population through its effects. It's slow work, it's careful work, and it's how we're going to bridge the gap between what we can see and what's actually there. I want to close with one more reflection, because I think it's important for understanding not just the science, but what this moment actually represents in the larger arc of how humans relate to space. For most of history, we thought of the night sky as a fixed canvas. The stars moved in predictable ways. The planets wandered, but they were knowable. Anything that appeared suddenly, like a comet or a meteor, was treated as an omen, a portent, a message from something beyond our understanding. We've come a long way from that. We now understand that the sky is dynamic, that near-Earth space is populated with moving bodies, that our orbital environment is an ecosystem in its own right. But we're still discovering how much of that ecosystem we haven't mapped. We're still finding objects whose existence we only infer. We're still flying blind in regions of the sky that our instruments simply cannot reach. The sense of mystery hasn't been eliminated by science. It's been refined, narrowed, focused into specific questions we can answer with better data. What this week represents, in that longer arc, is a kind of threshold crossing. For the first time, we've clearly detected the influence of a hidden asteroid population through its effects alone. We have an existence proof. The blind zone is populated, the objects in it are active, and our relationship with those objects is going to get more detailed, more quantitative, and more real over the coming years as our instruments catch up to our inferences. The two asteroids that will skim past Earth tomorrow are not the story. The 4.5 Sigma anomaly is only part of the story. The peer-reviewed paper is the structural centre of the story, but even that isn't the whole thing. The whole story, the one worth remembering, is about a detection gap that has been hiding a population of active objects from us for as long as we've been able to look at the sky. And it's about the moment, which is happening right now, when that population finally started to reveal itself through the patient accumulation of evidence. We are not reacting to what's coming toward Earth. We are reacting to what Earth has already been moving through without ever seeing it. That's what this week is really about. That's what Schober's paper documented. That's what the AMS has been logging in their Fireball data. That's what the hidden parent of M2026 A1 represents. Not a threat, not an emergency, but a revelation. A revelation about the limits of what we can see and about how much of the world around us operates in places we haven't figured out how to look yet. The sky is busier than our catalogues suggest. It always has been. The difference now is that we're starting to know it. And knowing, even without seeing, is the first step toward understanding. The invisible asteroid feeding Earth's skies has been there all along. It just took a convergence of evidence, a careful scientist, and a fortuitous week of flybys for us to finally notice that it was there. What comes next is going to be even more interesting, because if one is there, others are too. And the question isn't whether we'll find them. The question is how many and how soon and what they'll tell us about the parts of the sky we're only just beginning to see. The next time you look up, remember that what you're seeing is only a fraction of what's actually there. And the fraction that's hidden, the one behind the sun's glare, the one in the blind zone, the one that has been quietly influencing Earth's environment for longer than we've been alive, is finally, slowly, starting to become visible, not through direct observation, not through any telescope we've ever built, but through the light of its own debris, burning up in our atmosphere, telling us in the oldest language the universe knows that we've been sharing our corner of space with something we never knew was there. And that, more than any single flyby, more than any single paper, more than any single anomaly, is what makes this week worth paying attention to. Not because the sky is falling, but because, for the first time, we're starting to see what's always been in it. Thanks for staying with me. Stay curious. Keep looking up, and remember, the story of space isn't about what we've mapped, it's about what's still waiting to be found, and the next discovery might already be on its way in the form of a streak of light, arriving from a place we haven't learned how to look yet,